Hello everyone, and welcome to our May Bash. So the theme of this bash is machine learning, viewed from a wide variety of different perspectives. We've got 4 excellent presenters and talks lined up, not in any particular order, apart from how confident they were about staying within the time limit. But just before we begin, just to say we have the next 2 events lined up, and hopefully we'll be announcing those soon. And as always, thanks in advance to our speakers, to Zara and Ryan for doing all the hard work in the background, and to yourselves for attending yet another Zoom meeting on a Friday. So we will try and make it worth your while. So without further ado, I'd like to call on Fran to deliver our first talk. Hello there and welcome to Bash.
Hello.
Hello. The floor is yours. Yeah.
Thank you very much. So I'm going to just give us a high-level overview of some stats, data science, the entire history of computing, try and work out what it all means and how we can help each other. I guess train of thought kicked off by various discussions on Twitter where I spend far too much time. Everyone needs programmers to appreciate statistics and vice versa for the statisticians to understand some of the low-level stuff. I think throughout my career, I've seen a disconnect between people doing the maths and the stats and the data science and the machine learning. Maybe they've got a strategic spreadsheet on their machine and people trying to productionize things. And well, why does it take 6 months to do something I can do in half an hour? We tend to bicker with each other, and I think we should start talking to each other and learn from each other. The history of AI and machine learning is completely entwined with computing. We wouldn't have one without the other. So let's take a long view of things and see what we can learn. Begs the question, what is a computer? This is really fundamental, and I could wax lyrical about this for ages. But you can see a move through time for machines that do specific things, like weaving, that you can program by giving them different card configurations to come out of different patterns. And you move towards Babbage's difference engine that does one specific thing, and the idea of a much more general machine that can do anything. If you look through the history of computing, you see just gradual little changes, maybe Hollerith's tabulator, which was to do with counting votes, moving in to give you punch cards, and then lots of things start happening around World War II. It's just some background there. The main takeaway from this slide is just that computers are machines that could do almost anything. But once you've got computers, then you can code them to do almost anything. This has some implications. Don't know if anyone's come across Konrad Zuse before. Well, revisit the name in a slide or 2. But he made the point that if you start storing data and the programs in the same space as the data, then the program can operate on itself. And if that program can operate on itself, well, whether that's making a contract with the devil as he saw it or not, it does allow us some possibilities. He introduced some simple building blocks, like the idea of being able to write procedures to piece things together. He introduced the first real programming language, according to the internet, way back in 1944 or so, as computers were just becoming a thing. But like I said, he introduced the idea of procedures. So instead of just having a card that gave you loads of instructions, you break it up in blocks, and that helps us understand what's happening. He knew that they could do much more arithmetic than arithmetic, and he was aware of a lot of people viewing computers as just calculators. I don't think people had pocket calculators commonly back then. Anyway, that's another story. So that was a brief history of computers going from looms up to World War II and then programming languages and beyond. I said I was going to talk about machine learning and AI. Where was the AI in that? It was hiding in the background. In fact, some of it predates the computers and the things I just talked about. I don't know if you come across Hilbert's program, that was an attempt to formalise all of mathematics and ask the question, could you kind of automatically work out every single possible maths theorem, work out whether they were true or false, and make sure you'd got a complete set of all the maths that there was and didn't involve any inconsistencies? With the idea, I guess, that you could automate this somehow before you got computers to automate things. Kerr Gödel throws a spanner in the works and shows you can't have that consistency and completeness going on. And then people start going off on a sidetrack and wondering what you can actually compute and calculate. You end up with a church Turing thesis, which is talking about what you can reason about, what you can represent with noughts and ones. Again, that would be another separate talk. But that's a pivotal moment. We start moving towards, well, what can we do with these computers? And then here we go. There's where the AI comes in. A guy called Arthur Samuel teaches his computer to play checkers, or as we might call it over here, drafts, in 1954. 2 years later, John McCarthy calls together people for an academic workshop and coins the phrase artificial intelligence. So we've got machine learning predating AI as a phrase. And just see how old this is and think about how common computers were then. We're investigating what was effectively computable before we actually commonly had computers. Just saying. So, okay, I've said where was the AI. Do we know what AI actually is? Again, we see some things kicking off from trains of thought and explorations in World War II. Some of the earliest stuff involves John von Neumann, who you may know from some famous computer architectures, another guy called Stanislav Ulam, were playing around with cellular automaton. So you set up some rules. So Conway's Game of Life is an example. Things can move or grow or breed and just see what happens. So it's like you've created an artificial universe and explore what goes on. We talked about using a computer to play drafts or checkers. There's a lot of recurrent themes of game playing happening in the background with AI. But then it moves on to other things. They can calculate things for us. Maybe they can speak. If you look for the history of AI, you'll see an early stage where a lot of expert systems. So you'd sit down with an expert in a domain area and try and write down all the rules the human was doing and then get the computer to apply those rules. But things have moved on to much broader things now because we've got more compute power. You can see image recognition happening, natural language processing, and we are tending to still have some specific tasks going on, like can I label the cats or dogs in this photo, rather than more general, what can I see in the clouds and things. So where we had that specific machines and more general purpose machines, in AI you have the idea of specific tasks versus the idea of a general intelligence. And then you've got a software version versus a hardware version. If anyone's ever played around with Python turtle graphics, that dates right back to a little robot turtle in the 1940s that moved around and could avoid collisions. So I see these things going around in recurring themes and circles. We tend to forget history. If you look through the history of AI, we had this expert systems promising loads of things, and then it didn't deliver on the promise. So I think we can learn if we look back at history. Most people have forgotten about Zeus, and a lot of people have forgotten that some of the first coders were female. There's interesting things in history, but there's not time to go through all of it. Just a little glimmer for you. Go read up more if you want. You might learn something, even if the machines don't. So is AI snake oil? I've said that we've seen some cool things happening in the past, but then we've had this AI winter where it was all overpromised. And I've recently been seeing a lot of startup companies claiming they're using AI. AI is used as a label to get funding and sell stuff. People do fall for it. The AI is often a lie, but it's not really snake oil. Sometimes people claim they're using AI and they jolly well aren't. we have managed to do some cool stuff. We've automated a lot of things. I mentioned labeling photos. Translating between natural languages has started by just building up from the ground, the machine guessing, human giving feedback and making it better. And that's really useful tech nowadays. There's loads of AI in games. If you're got a gaming rig and like playing games, computer games, there's some AI happening in the background there. And then I mentioned drafts, and then we see chess, and then we see Go. There's some interesting things there. Go read about it or talk to me if you want more details. And the other things fall under the remit of AI as well, such as things called nature-inspired algorithms. And I could give you a more in-depth talk about that at some point. Robots can save people's lives. Image recognition can spot tumours. So AI isn't purely snake oil. It's used like that sometimes, though. What you tend to see, and the same happens with philosophy and other branches of knowledge, is that when you get something specific working, it tends to be called something else. So we start talking about image recognition instead of AI, and then you end up with a new discipline or field. So what's left in AI is we're not quite sure what this is, and lots of questions. Yeah, I mentioned AI, machine learning. I mentioned Arthur Samuel introducing the phrase ages ago. So he wanted his computer to play drafts or checkers with him. And he gave it some input on some games that had been written up. And it just tried stuff out at random. And it either won or lost. And it used that to try and drive how it played next time. So it was this feedback loop or a for loop, trying some random stuff, seeing what happened, and then trying to incrementally improve. And that is my summary of all AI and machine learning. For loop, try something random, get some feedback, and iteratively improve. That's all there is to it. I could finish there, but I call this regression to mediocrity. A lot of people claim machine learning is learning from data. That can be true, but there's more to it than that. Sometimes you just rudely call it curve fitting or regression instead. Let's just hold in mind the bigger picture that the games, the checkers, drafts, Go, all kinds of other things is imperative for learning. If you want to learn stuff, playing a game's often the way to do it. So I challenge you to find a toy problem or a game and to learn to code better and explore machine learning. I've written a book where it's got loads of things that you can play around with if you want to learn more about some machine learning stuff. However, let's cut to the chase. Curve fitting. So I would feel far better if I was in the room and could see what people around me were nodding their heads at and what people knew and didn't know. But here's an example of some curve fitting from Stack Overflow's blog. Did you know that people who code and use spaces tend to make more money than those who use tabs? You can fit a straight line to the data and you can see one curve's higher than the other. This curve fitting is known as regression, and we'll see why in a moment. We fit a line through the points, and we try and work out how slopey it is and how high up it is. And I think we all know that just because we can find a good measure of our correlation and fit things quite closely, that doesn't tell us that's causing things. If you put spaces in your code, you will not get a pay rise. We know that, right? You're all nodding. I can see that. Why is it called regression? Line or curve fitting would work. Well, again, some long history. A guy called Francis Galton gave a talk in 1877, spotting that if you had big plants and small plants and mixed the seeds up, they tended to all end up at this mediocre median average. And then he played around and looked at the heights of people and decided if you had taller parents, you tend to get shorter children and vice versa. Like there was some pull to this mediocre state. So he described this phenomenon as regressing or going back towards mediocrity. So he used all kinds of phrases about regression to mediocrity here. That's where we get the phrase from when we're doing curve fitting. There's a huge number of other people involved in the statistical revolution at the time. And the various elements of what they were investigating was somewhat unsavoury. I mean, not only are we looking at the height of people and going, oh, well, everyone tends to end up being mediocre height. You start looking at intelligence that way as well and things. This is a dark, murky past. It did do some good, find out some cool things as well. Like if you want to guess how many sweets in a jar or guess the weight of an animal, the average can actually be useful and good. So mediocre and mean and medians aren't always bad. Neural networks are the next step in this curve-fitting machine learning view of the world. They've got a really, really long history that definitely predates computers, where people are trying to think, if I pass electricity through stuff, will it automatically start thinking? So long history there. Some people would regard some neural networks as a type of curve fitting or regression as well. Now, let's just start wrapping things up. We've done a zoom through everything. We're seeing some new things like the image recognition because of greater compute power. And yet some of this is still redoing some old stuff from a long time ago. So don't let the new toys, something being called data science or the cloud your judgment. If you're a dev, don't forget what you already know about writing good code. Let's not regress to mediocrity, even if we're just curve fitting. So let's go back to the worlds colliding again, the statisticians and the devs talking to each other. You might just have a strategic spreadsheet or a script or have a prototype or so on. Don't say just. That's asking for trouble. If you're writing some notebook, do you use Control-Z to wind back if something goes wrong? Use version control, right? Don't go backwards on this. Things are called Jupyter notebooks or Databricks notebooks based on the idea of a lab notebook. The point of that is to keep a record of what you've done so other people can take up your experiments. Wherever you think Da Vinci's lab notebook is in fact clear and legible with his backwards writing is another matter. But is your code clear and legible? Functions. Zeus introduced the idea of procedures. Embrace functions. Don't just have a spew of commands. That makes things more legible. Watch out for code that's hard to test. If you call out to random in the middle of a function or date time now or open a file, that makes things hard to test. There's ways to make code better. So if you're a data scientist, talk to a developer about how to test code well, how to structure it. Let's learn from each other. I've talked about testing. This is another place where worlds collide. If a data scientist or someone doing machine learning say they've tested their model, they are meaning something very different to a developer saying they've tested their code. Testing code is about code that's doing the testing. You've got asserts that pass or fail. It documents how the code works. It catches regressions, things going backwards to how they were before. Testing a model's a different thing. You're evaluating the model. You're saying, is it good enough? I could look at the root mean squared error or the accuracy. So just because someone's using the same word as you, don't assume you know what they mean. Ask for more of a demo. Find out what they're talking about. Find out what's happening under the hood. How do you deploy things? That's something devs ought to be quite good at. So if you've got a notebook on your laptop, talk to someone else about how to get it in a place that can be shared, how to use version control. If you type it straight into Colab or one of the other cloud providers, have you got a backup of it somewhere? Can anyone else see it? Do you know what versions of NumPy or Pandas, if you're doing Python, you're using? Don't forget about requirements.txt. Make sure other people can rerun your scientific experiment. And whoever you are, whether you're a data scientist or a dev, do what you love. If you're a data scientist, flip your head a bit. And if you're using some libraries, spot things that you love and spot things that you find difficult to use. Maybe the docs aren't clear. Maybe there's incoherence between the order of parameters. Learn from the things you don't like and try and make your code better. Or if it's open source, submit a pull request to make it better. If you're a programmer and you don't understand data science, you don't know what this machine learning thing is, ask probing questions. You will be able to find out at least some of high level of what's going on, and you will be able to get involved, have fun, and make it better. So, as I said, don't let the cloud your judgment, and don't forget what we've learned about writing functions and some other basic things over the last, 60, 70 years of computers. Let's not regress towards mediocrity. So this talk, it was a whirlwind view of the history of computing, stats, everything. Let's dismiss what's mediocre. Devs, learn some data science. It's awesome. It's not rocket science, and it's loads of fun. And statisticians, learn some code craft. Learn to write functions well. Learn the joy of well-crafted code that does what you want. Find a toy problem. Practice. That was my call to arms. Let's give each other a helping hand. And I'm done. Back to you.
Brilliant. Thank you so much, and especially for giving me a lead back. That's always very much appreciated. If I can just ask a few questions. One for my own benefit. You mentioned the kind of winter of AI a couple of times, and
right.
I remember this well because in the early 90s I was doing a psychology degree, and we were learning more about neural nets than we were about Freud. And there was all this breathless anticipation, and our lecturers were assuring us that conscious machines were just around the corner. And in the computer science department, there was allegedly a neural net that was reading the newspapers every morning. And then it all went a bit quiet and everybody got very embarrassed for a few years, So just wondering if you could speak a little bit more to what happened there and why.
I think we were starting to do some cool stuff, but people, to stick with the statistics words, extrapolated wildly from a very small data point and went, oh, interesting stuff's coming just around the future. We could do this one small thing, so we'll be able to do all these other things. Now, if you're going to bring about some of the sci-fi goodness that I want to see from Star Trek of transporters and teleporters and the other good things, you need the imagination to think about what's possible. But you do end up with people riding on the back of it, using it to get funding out of people and not knowing what they're talking about and lying horribly. So be aware that with any kind of new tech, it gets over-promised, and we get it wrong the other way. I forget who famously said, well, I don't ever see there be more than 5 computers in the world. And, that was wrong. If you wind all the way back to Turing, he said, oh, well, within maybe 5-10 years, we'll have computers that can speak and interact with us rather than just play chess with us. The only thing that's holding us back is memory. We've got loads more RAM now, and that wasn't what was holding us back. So, people are wrong, people lie. That's all right, just watch what's happening. But yeah, watch out for people using words, peppering them around like snake oil, not knowing what they're talking about. Yeah,
very true. And then a question here from YouTube. So which of the big projects, DeepMind, OpenAI, etc., show the most promise in your opinion?
Oh, that's a really unfair question. At one point, something interesting happens, and then another interesting thing happens. I'm kind of watching all of them from the background. Well, one thing that's piqued my interest recently is, I think there's in the UK, it might be based in Oxford, though everything's virtual now because we've all fallen into the matrix, is the Institute for the Future of Humanity, which isn't like pushing some of the tech and doing the code and like labeling cats and dogs and other important AI stuff. That's delving into trying to find out some of the theoretical boundaries, which, as we've just said, is quite hard to, because you tend to be extrapolating. That's asking some questions about ethics and data and things. So I think it's called the Institute for the Future of Humanity, which is quite a grand sweeping thing. But that's a different steer than what the question's really asking about. It's all interesting. I'm not betting on any one of them. Things are change and keep changing.
Okay. Very good, very good. And then if I can ask another incredibly unfair and general question then. So whenever we're talking about the developer's role and the developer's responsibilities, and, whenever we do events like this, we get all kinds of perspectives. And some people say, oh, we've drifted from math and it should all be about algorithms and good design and so on. And then we get other people saying, no, it's all about product these days and making the customer happy and building things that people actually want and need and so on. So where do you think the balance is going to land going forwards in terms of what the development job actually is?
I think you're going to keep having a parallel strands. You do need some hardcore geekery with people doing like blue sky research, finding out what's possible. And yet computers, as they're becoming more and more all pervasive, you're having things between speculatively written apps for your phone or whatever that you guess what customers might want that can be monetized. And then you've got other people who are doing things that do need doing, like, for example, a functioning track and trace system. That needs some depth in the background, and you need some testing there. And you could sometimes what the customer wants is right in that kind of thing. Sometimes they're wrong. Wind it all the way back from this. If we're going to keep having people tapping away at keyboards, then this is a people problem, right? Theoretically, and I've done this before, only with FizzBuzz, admittedly. When I mentioned about Zeus talking about self-modifying code, you could make the computers program themselves, and then they could control like hardware generating plants and factories. And then we could have Skynet. And then, but I mean, maybe the dream would be if you've got customers who want specific things, they write BDD style tests and the AI generates code that does exactly what the customer wanted. So we can go off and play some games instead. I think that would be living the dream.
Very good. Thank you. Right. Sadly, I think we're at time. So if I can thank you so much and dismiss you at this point. So
a pleasure.
Thank you. We will bring you back at the end for the any questions section. But if I can ask Colin onto the stage, please. Thank you. And the floor is yours, sir.
Thank you very much. So thank you, everyone, for joining us. My name's Colin Gillespie, and I'm going to talk about you want to get started with AI, which is a slight variation to the title I originally had, but the content's more or less the same. So a little bit about me. I work at a company as a co-founder of a company called Jumping Rivers. We're a data science, machine learning, AI consultancy. We do lots of R, we do lots of Python, machine learning, AI infrastructure training. And we also have the prize for the most mysterious name in machine learning as well. So we think we're a well-rounded company. In terms of my background, I'm a part-time academic, and I can hear the audience saying aren't all academics, but I'm officially part-time, and I'm a stats lecturer over at Newcastle University. And midway between sort of PhD and lecturing, I did a postdoc many years ago on, I suppose it was cloud computing without the cloud being around. So I had SOAP web services and databases and all sorts of geeky computing stuff. And that's how I sort of got married up with sort of statistics, machine learning, and computing, having that background. And a quick plug for a job. We're advertising a role at Jumping Rivers. So you can either ping me an email afterwards or go to that website. And the job is either sort of beginning or towards sort of the middle of career in terms of R or Python. So if you're interested, please visit the website or ping me. Right. Personally, AI and machine learning are amazing, right? So it always stuns me that when you go to Google and you start typing something, it searches all these billions of websites instantaneously and gives you something pretty good. And I might understand the technology to a certain extent, but it's just amazing. You know, it's just amazing in terms of computation. It's amazing in terms of AI and machine learning. It's just pretty cool. You know, I'm just stunned. But there's always a but, right? Otherwise, the talk would be a bit boring. I came across this article, right? This article was published, so it's all about using real-world data and AI. I'm not quite sure what non-real-world data is, but it's using real-world data and AI on oncology trials, right? So I would say it's an important topic. It was published, 6-7 weeks ago, so it's pretty new. It was published in Nature, right? So Nature is sort of the preeminent journal in academia, and it's not Nature Total Landscaping either. It's not in between a crematorium and an adult bookshop. It is the proper journal. And when you sort of see that title, when I seen that title, I was thinking, well, what sort of AI would they be doing? Neural nets? Yeah. TensorFlow? Almost certainly. Definitely some cloud computing. Lots of GPUs. There must just be GPUs everywhere. That's the sort of stuff they're going to be doing. And I had a pretty good idea of the sort of techniques they'll be using. And then you read the methods section, and it used the logistic regression model. We teach that, in my academic part, we teach that in first year of a statistics degree. And that's quite a contrast between sort of AI in the cloud, doing GPUs, doing amazing stuff, and first year stats, right? And I'm not even cherry picking out, this is the most sophisticated mathematics of this paper. And there's nothing wrong with what they've done, right? There's clearly nothing wrong with the topic that they're looking at, right? I think we'd all agree that this is a good topic. And there's nothing wrong with the solution that they've used. If the solution works, who cares? But the problem is, this over-reporting increases the AI bubble, right? It makes it really hard to figure out what people are doing and what people should be doing. And it sort of keeps up this sort of, we need to keep up with the AI Joneses. Well, that bunch over there, they're doing AI, so we want to do it. We don't really know what AI is, but we want to do it because they're doing it. And it sort of makes this sort of cycle, and it sort of devalues the discipline. And both in academia and at Jumping Rivers, we work with lots of companies, and companies in AI is also sort of an interesting thing. It's the trouble is they believe a lot of this hype, and I can understand why. If your competitor is saying we're doing cutting edge machine learning, we're doing cutting edge AI, you're not going to say, well, we don't. We just do something quite easy and straightforward, and it's not that hard. So we've sort of got ourselves into a bit of a hype. The hype, there's definitely something there because, well, Google is just amazing. But then it's sort of mixed in with all sorts of different bits and pieces. And that gets a bit tricky. So.
Hello, IT. Something's wrong with my computer. Have you tried turning it off and on again? No, all clear. Thanks. You're welcome, mate. Hello, IT.
Tried turning it off and on again and nothing happens.
Is it definitely plugged in?
Let me have a look. Sorry, that's it. Thanks very much.
You're welcome, mate.
So this is one of my favourite clips from the IT crowd, except when it goes again. And to me, this is the perfect solution, right? They've come up with the perfect solution, right? It's easy and cheap, right? It just requires, a tape recorder. It's scalable, right? This is perfect. You just buy more tape recorders and it just scales. We could get to parallel computing, but it scales. It's perfect. It's wonderful. And it solves most problems. I'm sure if you ever had to help someone with IT, and I suspect most of the audience has, the first thing you do is, well, have you tried turning it off and on again? Followed by, have you tried Googling for it? That's the two suggestions you would always give. But it's not AI, but it works. Now, I've got a little story for you. And this story may or may not be true, and it may or may not have happened in 2009, around about the autumn time. So take what you want from that. And we were invited to do a sort of standard AI pitch, hackathon, that sort of stuff. And we've done quite a few of these, sort of humble brag. We've done 5 of them and won 4. So we're quite proud. The one we didn't win was the one that I attended by myself, so somewhat embarrassing. But we're quite good at these. And typically what happens is the company describes their problem, right? So they take you through the problem and what they want you to solve. And the trouble with this is, trouble's a wrong word, but the issue is they're also leading you through the solution that they sort of want to take, right? And typically, as you might imagine, it's going to be a sort of AI solution. And the people taking you through this problem are not stupid. They're typically very clever, have a strong background in computing, mathematics, statistics, there's a whole group. And so, they've tried all the obvious stuff, but they're still thinking that you have some magic sauce or magic powder that you can just sprinkle on and all the issues will just disappear and you can help them. And in this particular pitch, it was about predictive maintenance. So it was a massive factory, right? Absolutely huge factory. And there was lots of machines, and essentially when a machine broke, it cost lots of money, right? So a machine breaking down was a major deal because part A of the factory depended on part B, B depended on C. So it was this huge, massive pipeline. And so if one thing broke, it cost them stupendous amounts of cash. And so what they're wanting is, can we predict the ones that break, right? Predictive maintenance. And you can imagine all the data that they have, historical data, what's broken, when it's broken, the person who's operating the machine, what sort of stuff was doing, the weather, and then just everything else in the day, right? All this data. And you think, oh, this is clearly an AI problem, right? If there was an AI problem, this is it. You've got all this data, they've got Internet of Things connected to machines, so you've got vibrations, temperature, you've got everything, and that's what they want to do. It's a great AI. And so this is wonderful. So every day in our company started to think about the algorithms, look at all those lovely algorithms we could do. We could do some trees. And what's better than trees? Well, we can make them boosted, because we always like some boosted trees, because that's what you want. And then we can make them baggy. But we want to win this thing, so clearly we want sort of deep boosted baggy trees in the cloud. Just sort of throw all this stuff into one sort of buzzword soup, give it a good stir, and off we go. And this was great. This was a good sort of AI data science problem, whatever you want to call it. But then disaster struck, right? So disaster did strike. And this happens quite often, if I'm honest. And it's not pleasant. It's something you expect. You've got this model, you've got this structure in your mind, you've got the perfect solution, and then you make the mistake of talking to the domain experts. And these folk always spoil your fun, right? Regardless if you're in data science, if you're constructing a web page or whatever, they always spoil the fun. We've got the solution. Why do they have to just come and annoy us with some additional knowledge that we didn't really need? So, well, what did we do? They pointed out the one key problem that they had, right? So they've got one key problem. And that key problem is that when the machine breaks, they can't find the instruction manual. Right? So they've gone to this whole expense of getting companies in, gone to the whole expense of pitching, gone to the whole expense of trying to figure out what sort of data. And actually, the problem that the people on the floor were saying is, well, when the machine breaks, it could take us hours to find the instruction manual to fix the machine. And you think, what? We can solve that problem. That problem is easy, right? That problem involves finding all the instruction manuals, putting it in a filing cabinet or putting it in a database or putting it somewhere, going around all the machines, giving them a little QR code or some number. We can solve that. And in fact, I suspect most people in audience could solve that. And the trouble was that it wasn't AI. It wasn't machine learning. It wasn't data science. And so therefore it would come from a different budget. And this is a reoccurring sort of, I suppose, scenario that we come up with. You know, and another story, and this is one of my favourites, was we were working with an oil company, and they were interested in sort of incorporating data and AI, and they were going around the country with VR goggles to show how amazing they were. And these VR goggles were cool, you know, they're really neat things. But they also sent someone in a helicopter to an oil rig with a clipboard and pen to write down some stuff, to then fly them back, to then type it up. And you think, could you not make that process a little better? You know, you don't need sophisticated techniques to solve that process. And it's a different budget. So typically when we're doing this stuff, there's always a data problem, right? There's always a data problem, and this is important, right? And when you're coming across a data problem, you should always try and solve this first. And the data problem is usually hard.
Ariam, how are we doing on the data core audit?
The probe used multiple SQL injections, but I've yet to find any compromised files.
Right. So the data problem is so hard that in 400 years from now, they're still having problem with SQL, right? This is how hard data is, right? It's not going to go away. It's tricky. It's hard.
Ariam,
And I can't work YouTube embedded in Google Slides. So whenever we start chatting with a new client, new customer, and we're talking about machine learning, we're talking about AI, one of the sort of the strategies that I now use, and when thinking about the problem, is to sort of have a thought process of, well, you want to predict next week's sales, right? You know, which shop wouldn't want to predict next week's sales? You know, that's a sensible thing. Can you tell me about what happened yesterday? How much did you sell? And if you can't answer that question, then don't worry about next week. You know, solve the thing that happened yesterday. You know, that's just easy machine learning because you're just counting things. Or you're wanting to do predictive maintenance. How many machines do you have that are currently broken? Right? And if you can't answer that question, why are you trying to predict what's going to happen next week? Because you need to know how much is broken just now. Or you wanted to predict your house price. Well, what is your house currently worth? And again, if you can't tell me that information just now, you know, what's the current state of play in your system, whatever that may be, then don't worry about this prediction. Sort what's currently happening. So you might remember this from last year. So this was Public Health in England, and this was September. And this was showing you the number of coronavirus cases reported by date. And what we can see is that on the sort of the right hand side, we've got the sort of the light blue, the cases that were announced, the cases that they found out about, that have been published, and then we've got the dark blue, the missing cases added have been added. And if you sort of cast your eye across from left to right, you can sort of see a horizontal line of where that sort of cut off occurs. You know, there seems to be a maximum value. And this was just counting cases, right? So around about that time, you might have remembered there was lots of modelling going on of, can we predict what's happening in the country next week, in a fortnight, next month, at Christmas? Lots of people trying to predict that. Track and Trace was trying to use this data, right? Lots of sophisticated algorithms, modelling was going on using this data. And this sort of meltdown, it was called, was caused because Public Health England were using an Excel spreadsheet and it reached its maximum size. So essentially it had too many rows in the spreadsheet and so it failed to update. Now, we work a lot with public health bodies, and by no means is the people doing this to blame. You know, it's sort of an infrastructure part, right? In the same way that if security goes down on a website, it tends to be higher up, it's a maintenance thing. But here we weren't counting the number of cases of coronavirus, and then that had massive impact. And perhaps even more depressingly was, well, the solution to this was, well, the technical issue has now been resolved by splitting Excel files into batches. Okay, then I suppose that did work, but hopefully they've got a better solution now. But again, we had all this modelling, all this prediction. the entire economy and lives were being failed because we messed up the data. So just to end, I'd like to say, well, how do we start an AI project? So when clients come to us, how do we start an AI project? What does that process look like? And not only do I start with, what can you tell me about today's data? I quite like this question, right? Assume that AI is magic and money is no problem, right? So you've got all the money in the world and AI is magic. You can do whatever you want. What do you want to happen? Right? What is the problem you're trying to solve? Right? Not the techniques you're trying to use or the infrastructure you're trying to use, but just what would you want? What do you want it to tell you? What do you want to optimize? What do you want to predict? Right? And that's quite nice because it sort of gets away from we want to use AI because everyone else is, right? There's no AI here. It's just, well, what's the problem you want to solve and how, what do you want to get out of that? So our typical workflow of when we're engaging is asking that question, what's the ideal solution? Right? What do you want to happen? Who'd be impacted by this solution? So quite often we deal with, I suppose, data science teams, right? And data science teams within companies, particularly even large companies, might only be 3 or 4 people. And a data scientist is typically expected to know everything in the world. So your average data science will be expected to know about statistics, maths, and machine learning, AI. They'd also be expected to know about code review, Git, Docker. They would also be expected to be quite good at Python, know about unit tests. They'll be building dashboards, so all of a sudden they're now expected to be web developers. And so trying to sort of pull apart who's in the larger organization. So you want to host a dashboard, well, what does your IT department say about that? Right? Or you're wanting to tell about this, well, where does that data come from? Who are the domain experts? So try and sort of pull in all that stuff together. Then we try and look at the data, right? So we'd like access to the data, and everyone we talk to always says wonderful data. Spoiler, it's never wonderful. There's always issues, right? That's fine. That's just the way things are. We're also interested in ease of access, right? If it takes 3 weeks for us to get access to our data, how do you expect us to build some sort of magical machine learning pipeline that predicts, how do we get that sort of flow? We want to think about data cleanliness, right? Is the data correct? We were doing some analysis on Wi-Fi connections last year, and we had values from all over the place, sort of minus 10,000 to 10,000, that was the number of users. And it was just, some of the data just really didn't make sense. So we had to figure out what was going on there. We'll then construct simple baseline models. So that may be some sort of regression model, a logistic regression. And for lots of companies, that's good enough, right? Because what they tend to have is they have 100 problems that need solved. So if they can get something that's pretty good, rather than making that absolutely fantastic, we can then move on to another problem and help them out with that. If it's sort of critical or they're really wanting to improve, then we can start looking at sophisticated techniques. Right? But that's at the end of a process. Right? It's at the end of, we know about the data, we understand the data, we know who's going to be impacted by the data, and we also have a baseline, right? That baseline of, so we can say, well, is this better? And so that's typically what we do for a sort of an AI interaction with a client. So in summary, data is key, right? If your data is hopeless, then doing sophisticated modeling is hard. I'm going to clarify that your data can contain errors, but as long as we know what those errors are and we can then impact them. So in the Wi-Fi issue, if we were getting ridiculous numbers of users, it was then an indication that something was wrong, right? So the data was wrong, but it was informative, right? And that's not the same as just not being able to access it. Know what you're wanting to solve, and then also build the right foundations. So what Fran was talking about right at the end was, it's sort of easy to build a model. It's really, really hard to get it to work week after week, month after month, and embed it into a larger organization. And that involves all the usual sort of software principles, unit tests, version control, all those sorts of things. And sort of going from your notebook, where you've got a proof of concept, to something that works, to something that's robust, isn't trivial. So thank you very much. If you're interested in anything that I've talked about, then by all means drop me an email. Also, that job, please ping me again and we can chat as well. Thank you.
Thank you so much. It was a wonderful talk. So just to ask a few questions. So first of all, is this the oldest problem IT in the new guys? In other words, if you think back to the difference engine and Charles Babbage and the maybe apocryphal story of somebody asking him, if we put in the wrong data, do we get the right results? So we're always looking for somebody to do the clever bit. We're always looking for something that will take away do the inspiration and the clever thinking and so on for us. So is AI just that desire coming around again?
I don't think that desire ever went away. I think it's also important to separate out AI, which is, Google, who are dealing with, ridiculous amounts of data that probably most of us couldn't even imagine how to deal with, and then sort of inconvenient data that's a bit annoying, a bit big, but we can all figure out how to work with it. And I think for most, not everyone obviously, but for most companies, they have that inconvenient data, and they usually have someone sitting in the corner with an Excel spreadsheet who just gets inspiration from the tea leaves and looking at the columns. And just clearly a computer can do better. Whatever you want to say, a computer can just do better than the person with the tea leaves in the spreadsheet.
Fair enough. Yeah, cool, good. So then, do you have, well, two-part question, and I think you touched on this at the end. Do you have a checklist for when you really wouldn't advise AI and you just immediately advise that the client just, run away from the whole idea? And a slightly unfair question, are there times when you've used it simply because that was just what the client insisted on, even though, other options would have been possible?
So I think all the hackathons we've won typically are AI hackathons, and we've won them by not doing anything AI. So there was one about essentially predicting leaks at Northumbrian Water. And you can imagine how you've got all the data in pipe type and soil type and historical data. And actually what they wanted to do was save money, which was fair enough. And so our solution was building a dashboard where they got all that data, and rather than the engineering spending 3 hours in the morning looking at the data, they spend 10 minutes. 45 engineers saving 3 hours a day. That's a lot of money, right?
Sure.
And that's an easy problem that we can solve. The other one's hard, but you need that first one before you do the second one. The other one, yes, and that's partly because my first ever client engagement when we started Jumping Rivers was, we can do some regression, some statistics, and then I got a phone call 3 weeks later saying, we've decided to go down the machine learning route. And that was just, so yeah, you're always honest with who we're dealing with, but obviously there has to be a bit of, I suppose, presentation.
Sure. And then one final one, just to keep us on time. So, but both yourself and Fran touched on the issue of testability, where if you're doing ML, you can test a model to a certain extent, but because there isn't like a defined stepwise algorithm, you can just say, it's doing good as far as we know. So there's different notions of testability in like mainstream software engineering and machine learning. How much does that matter in your experience in terms of do clients need one definition of testability rather than the other?
The big problem is that testing is now stochastic. So it's nice writing lots of unit tests where things are much more deterministic. You've got your add function 1 + 1 = 2, and it's going to do that tomorrow. If you've got a machine learning algorithm, then you've probably built that model using some sort of stochastic search algorithm. So just by definition, you run it again, you're going to get a different answer. And then also turns out the data changes, so you have more data tomorrow. So again, you're going to get different. So it's sort of the same testing procedure, but does have very odd and really hard edge cases that aren't sort of covered for the most part. And then that's also, you've got an assumption of the data that you're looking at today is statistically the same as yesterday. And by that, I mean that it's not been a massive spike in the Bitcoin price and you're trying to model Bitcoin. You're assuming that sort of roughly everything's all the same. And Elon hasn't tweeted out, buy Bitcoin. And then again, how do you handle that? Something has fundamentally changed. And that, again, that's also tricky.
Sure.
So yeah, it's got same testing, but additional stuff is also needed.
Very good. Cool. Well, listen, thank you so much. We shall bring you back at the end for the session with everybody. But if I can dismiss you for now, and if I can invite Vicky to step up virtually, as it were. Hi there.
Hi. Thanks.
The floor is yours. Yeah.
Okay. Thanks very much. Yeah. So today I'm going to talk about my journey as an engineer into machine learning. So first of all, I'll just start with a bit of a background on who I am. So I actually did my undergrad in physics at Queen's University Belfast, and I really enjoyed it. So I stayed on to do a PhD in exoplanet research. And my PhD was about trying to solve a problem in exoplanet detection using software and data. And I realized at the end of my PhD, I really enjoyed solving problems with software. And so I noticed that Liberty IT were hiring folks on their STEM track. So I applied and got the job, thankfully. And so I've been with Liberty IT ever since, and that is now 9.5 years, which is quite a scary thought. Most of my time at Liberty IT has been around developing web applications to help our parent company, Liberty Mutual Insurance. But then back in 2019, I got really interested in data science and machine learning. I started to read things and blog posts and stuff, and it sounded really similar to my PhD sort of research, using data to solve problems and software. So I spoke to my manager, and it turned out that Liberty IT were actually using Jumping Rivers. So thanks, Colin, to do a course on ML within their Belfast office. So my manager put me on that course, and I just loved it. And it was just right up my street. I love looking at data, I love analyzing it, and I love trying to solve problems with it. So it really got me hooked. And so I spent a lot of time personally, in the evenings and weekends, reading different books, doing different courses online, and trying to teach myself a bit more about data science and machine learning. And I spoke to, my managers in Liberty IT about opportunities within the company. And so for the last 1.5 years, I've got the opportunity to work on projects within Liberty IT around machine learning and data science. And so I'm working as an engineer with data scientists trying to solve problems together. And that's a really nice combination. Because we have the engineering excellence background that I have, and then their statistics and mathematical background. So we're kind of learning from each other in those projects, which is brilliant. And Liberty IT also sponsored me to do a postgraduate certificate in artificial intelligence at the Ulster University. So this was a part-time course that I did from July 2020 to December 2020. And so I had to work full-time, or not quite full-time, but I was working in Liberty IT and then trying to do this course as well. So I did spend a lot of my evenings and weekends. But sure, what else was anyone to do in 2020? The year that shall not be named. So I thankfully passed that course in December, and I also got awarded the best overall performance as well, which was really nice after all the hard work. So you might be thinking at this point, what has insurance got to do with machine learning? So this is just a definition I pulled offline, but machine learning is the process of solving a problem by using a statistical model based on a data set. And so Fran already touched on this, and Colin a bit too. So just really to kind of show what that means in the plot here. If you get started in machine learning, you'll probably come across the Iris toy data set. It's one of the first early data sets that you'll see whenever you're starting out. And it's a data set that has labeled data. So you have plant petal width and petal length and stuff about plants, and then you have the species of that plant, so whether it's a Setosa or Virginica. And what you can do with that labeled data set then is you can apply classification statistical models to try and determine, based on some attributes like petal width and petal length, what the species of the plant is. And that's really to solve a problem. If you were to go out and measure a plant petal width and petal length, then you could just determine the species based on that data. And so what the statistical model that I'm showing in the plot here is a support vector machine model. And essentially what it does is it looks at the data set you provide it, and it looks to try and find boundary lines to separate out the different classes, the different plant species. And so you can see that with the colors in the plot. So if I was to come along with a plant that I didn't know what species it was, and I knew the width was 2 and the length was 6, then this model would tell me it was Virginica. So Liberty Mutual Insurance has been around for over 100 years. And so we have a lot of big data. We have high volumes, high variability, and high velocity data. So we can really harness that data to try and solve some problems for our customers. And so some of the things that we've done within Liberty IT and Liberty Mutual is we've got image recognition models that allow a customer to take a picture, photos of their car after a car crash or accident. And then we run those images through a model, and we determine the scale of damage to the car. And using those models allows us to speed up the process for a customer to get their claim back. At the minute, one of the projects I'm working on is we're trying to enhance the customer experience when they're purchasing personal auto insurance in the US. And we're doing that using models to try and personalize the quote that they get through that process. So you might be wondering at this stage, how do you go about solving a problem with ML, with machine learning? And I think Colin really touched on it really well and talked about, sort of thought process that you go through. What I'm going to talk about is you've decided that ML is the right option. And so I'm going to talk about a typical machine learning workflow that you might see. And so I quite like this diagram because it kind of tells you the different processes. It kind of shows that it's an iterative process, and it tells you the different maybe roles that would be doing the jobs. So your business has a problem, and you think ML is going to be a good fit. So you'll work with a data scientist, and they'll collect necessary data to try and solve the problem. And they'll spend a lot of time cleaning and building features of that data, and then trying to come up with models that will solve the problem using that data. And they will validate those models and see if they are actually solving that business problem. And that is very iterative. And so you might have to go and collect more data because you realize that you don't have enough after you've trained the first couple of models, or you realize that you're missing an important feature and things like that. So that can take several months, if not longer, in the model development stage. But yay, you've got a model and it looks to be solving the business problem well. So you want to get it out there into production so that you can actually have the benefit of that model. And so you might actually just jump ahead to the last step there in the workflow, which is the inference step. So maybe it's a real-time model, and so you'll front it with an API, and you'll have an end-user application that'll send a request to that model and get a response back based on the prediction. And that's typically the work of like an ML engineer or a data engineer would usually do that. So that's a lot of work that I would do at times. And then you need to monitor that model in production because the data scientist has built that model at a point in time. And so they've built it on a data set at a point in time. So for example, say that the data that was used to build the model, you only had a small number of customers because your service hadn't been available for that long. And most of those customers were aged between 50 and 60 years. Now you've put that model out into production and you're getting a lot more traffic and there's a lot more customers using your service. And now the age distribution of your customers is between 30 years and 60 years. And so the model that you originally built is not going to work well with ages that it never saw before. And so that's where the bit in the middle comes in, like that training pipeline could be quite useful. So you have a pipeline that can get feedback from the model in production. And it can also get live data that's, as your model, as your production application is running and that data distribution is changing over time, it can get that. And it can be used to retrain the model. And then you can do some validation to see if the new model is better than the original model, and replace the model in production with that. And again, that's typically the role of an ML engineer or data engineer that would usually build out that piece of the step. So in the next couple of slides, I'm going to go into different parts of this process. I'm mainly going to focus on model development, just to give engineers and people watching this a bit of a more in-depth view of what that might look like. And then I'm going to talk about the whole workflow in the enterprise and my experience. So for model development, I'm going to actually talk about something that I did in my postgraduate AI course, and that's because it's not confidential, so I can share it more easily. So I actually looked at factors that could contribute to job satisfaction for developers. The reason I chose that was because I thought it was interesting, and also because KPMG's CIO survey found that CIOs have reported that there is a lack of skills of software engineers preventing their company from keeping up. So I thought it might be quite useful to see if I could find any factors that contributed to job satisfaction that could maybe help companies retain their staff or get new people in. So step number one is getting the data and preparing the data. So I saw that Stack Overflow actually run a developer survey for the last 10 years. And this survey actually includes things like job satisfaction, salary, and job role. And it's publicly available with the sensitive data removed. So this sounded like a good data set to solve my problem. So once I had my data set, then I had to do some initial exploratory data analysis just to see what it looked like. So I noticed that the number of questions varied over time. And you can see that from the bar chart here. So the darker the color of the bar, then the more questions there were in that year. So 2015 had the most questions. The number of responses also clearly varied over year. So that's shown by the height of the bar charts. So you can see that 2018, 2019, and 2020 had a lot more responses compared to previous years. And the format of the results as well varied. There was also high variability in the data too. So for example, one of the questions was about what languages you used as a developer. And you could there was something like 20 options and you could select multiple. And then I also noticed that the data had a class imbalance as well. So there was actually more satisfied developers in the data set than there was unsatisfied. So kind of taking all this into account, I decided then to focus just my analysis on the years 2018, 2019, and 2020. And the reason for that was because they were more consistent with the questions that they asked and the result format that they had. And they also had the most responses as well. So there was more data. So now I'd got my data set, I then had to start cleaning the data. So some of the things that I did was I had to rename columns for consistency across the years. I had to drop any duplicated data. I needed to bin some data for consistency as well, for example, ages. And then one of the biggest challenges I actually had was missing data. So this plot here is a missing data map. And it's just specifically for the 2018 data. And black shows you where data is missing, and grey is where data was there and present. So some things that you can do to handle missing data is you can just remove it. But I would have lost a lot of data if I had done that, so I don't want to do that option. Another option is you can impute it. So you could replace it with like a modal value or a median value, or you could even use another model to try and make a prediction on it. But what I ended up doing was I decided that as all my data was categorical, I just replaced the missing data with the missing category. And one of the reasons that I decided to do that was whenever I looked at the data, the missing data a bit more closely, I noticed that there was some trends between people from certain countries having more missing data than other countries and things like that. So I didn't want to lose anything about the missing data. So yay, I've got my clean data. So now I can start looking at training the model. And so before I can actually get into running a model, I need to select some features for the model. So I did that by visually checking how different features varied with developer satisfaction, and just to see if there was a visual correlation there. And then I also used the chi-square test of independence, which is a significance test, to see if there was any trends between the features and developer satisfaction. And so that helped me narrow down what features I passed through the models. And then this was really a classification problem. So I was trying to see if I could predict whether developers would be satisfied or not satisfied. So the models I used were just some really simple classification models, naive Bayes, decision tree, logistic regression, and k-nearest neighbor. And then I used accuracy, AUC, precision, and recall just to assess those models and evaluate their performance. And so you might notice that, I spent 3 slides talking about data preparation, and I've just got 1 slide here on training the model. And that's kind of indicative of like the amount of time that you will spend on data preparation versus the modeling. And so typically 90% of your time will be spent on data preparation. And so this is just a kind of screenshot of all the code that I had, which ended up being 900 lines for data preparation, versus the model code, which was only 100 lines. So it kind of gives you that nice 90-10% split. So what was my outcome of this? So whenever I put my data through those models that I had chosen and looked at the evaluation metrics, and I did that for each year individually because some of the years had slight variations on questions, and I also did it for all the years combined. I found that the performance of the models were not amazing, to be honest. And the best model overall was logistic regression model for the 2019 data. It had the best metrics for accuracy, AUC, precision, and recall. So I try to think, how could I improve my model? So one of the thoughts I had was the fact that I had an imbalanced data set. So I had a lot more satisfied developers versus unsatisfied. So I actually did this project in R. We use Python a lot more in Liberty IT for machine learning, but I was just keen to learn R as part of my uni course and just get a better handle on it. And so I used the SMOTE package in R to balance my data. So that's synthetic minority oversampling technique. And I did find that it did improve my models a bit, but they still weren't amazing. So that's maybe telling me that I either didn't have the right data or enough data or the right features. But again, I did find that the logistic regression 2019 model was still the better one out of all the other years. And so I thought I would look at the logistic regression model and what features it had ranked as having a higher impact on the model. So one of the questions in the 2019 data that was not in the other years was they asked developers about how confident they were in their manager. And so what this table is showing you is the features and then the logistic regression odds ratio for those features. So basically the higher number of the odds ratio, then the more impact that feature has on whether a developer was satisfied or not. And so it was interesting to see that the manager idiot feature did seem to have a big impact on the model, along with age, developer type, country, and things like that, which I saw in the other years too. So that's a nice toy example of me developing a model for my uni course. But what about whenever you get into enterprise and you're trying to do machine learning at an enterprise level? So this is stuff that I didn't learn in my uni course, and I didn't learn in the books or the courses that I found myself in my self-learning. And this is stuff that I really learned through my projects in Liberty IT. One of the biggest issues is reproducible research. So you've maybe heard Colin and Fran already mention that, you know, a lot of work can sometimes be done in notebooks, and it might not be in Git, which is real and does happen. And so it can make it hard to reproduce a model that someone's built. So one of the things that we use to try and help with this is MLflow. So MLflow has different components to it, and it has a tracking component. And it allows you to track your different experiments for building your model. So maybe you know, you'll track, you know, maybe you'll try different types of models, maybe you'll try tuning your model and hyperparameters, maybe you'll try different features, and it allows you to track all that and the performance metrics of each model as well. And then MLflow also gives you the ability to package up your model into an easily deployable artifact as well. So it can help with getting your model from research stage into production a lot faster too. So it can be quite useful for that. Whenever you're playing with toy models yourself in those courses, they're often quite small in size. But what we've seen in enterprise is that some of the models can get quite large, and they can be 10 or 20 gig. And so that can be quite a challenge to get them deployed out into production as well. And then often the best models are sometimes ensemble models. So an ensemble model is maybe where you'll have, you know, multiple decision trees, and you'll maybe run your data through those different decision trees, and then you'll make a decision at the end whether to what the prediction should be based on the output of all those different models. And sometimes you're maybe wanting to test model A versus model B in production, so you can determine which model is actually better. So maybe you'll want 50% of traffic going to model A and 50% going to model B. So you can assess whether you should use model A versus model B. And so you need to actually factor in routing logic like that whenever you're going to production with your models. And that can be quite a challenge. And Selden has some stuff there with their inference graph, which allows you to write that sort of routing logic as configuration for some of those issues. So it can be quite useful. And then oftentimes, like Colin, I think, mentioned, data is a big issue. So sometimes what you can see is that data scientists will be building their models with offline data, and they'll have a lot more data than you can get at real time from an API that they use. And so maybe they'll have built their model, the best performing model needs some external feature that you can't get at runtime from the external application that's calling your model. And so you might need to build in a way for the model to be able to reach out and get those external features from a database store. And so Amazon actually have a feature store which could be used for that. And so it allows you to call an API to get those external features in. And then you really need to monitor your model in production. So I kind of mentioned it whenever I talked about the ML workflow piece, but whenever you get your model out into production, it can deteriorate over time like anything. And so some of the things that you might want to look out for is data drift. And that drift in the distribution of the data you use to build your model. And so the cloud providers do give offerings to help with model monitoring itself and to help to know whether you need to retrain your model or not. So they do provide built-in monitoring tools. There is also the Great Expectations library, which is a Python open source library, which essentially allows you to create rules on your data, so you can detect things like data drift And so I've used that to kind of help with data drift monitoring as well. And then just generally making sure that enterprise engineering standards are applied. So whenever I've worked on the projects in Liberty IT, I've usually paired up with a data scientist, and together we've made sure that the code's been built in an enterprise standard way. We've had unit tests, and we've made sure there's other tests there, like the model monitoring tests, and just that it's in clean code standards. So wrapping up now, but I just want to call this out, is machine learning the answer to all our problems? And I think you've heard that in the talks today, that it's not always the answer. So it adds complexity and time to any project. And really be mindful, can you use a simpler solution? Would a rule-based solution be better? Is it even feasible for what you're trying to do? Can you get the data that you need to try and solve that problem? And also, ethics, is it okay what you're trying to do? So hopefully you still think that machine learning sounds awesome, and you're interested like me to get started in it. So I kind of point you to, so I haven't written any books or anything, but I did write a blog post last year with some other engineers from Liberty IT, and we just documented all the resources and tools that we found useful whenever we were starting out as engineers, trying to grow our knowledge in machine learning and data science. So it's a great place to go to see all those different resources for the different levels that you might be at. And also feel free to reach out to me on LinkedIn. I'm more than happy to chat about my experience and answer any questions. So that's it for me. So thanks, Gareth.
Cool. Awesome. Thank you so much. Just a few questions there. So from what you were saying, it sounded like a lot of the ML jobs you were doing were fairly well integrated into, standard cloud platforms and standard developer workflows and, monitoring and version control and testing and all this kind of thing. So how far down that particular road do you think we are? How much integration is there between the ML tool set and the tool set of a standard developer?
Yeah, I think we're still at the start of that journey, really. So I went to like a meetup before all the lockdowns happened, and a data science meetup, and they were really talking about, Git and things like that being new.
Mm-hmm.
So I think for engineers kind of doing ML, we can find the tools and the technologies, and we know how to integrate them from our background. But I think if data scientists are doing that sort of role, they don't have that knowledge or that skills, and they're quite early on in the journey. So I think it still needs to grow. Like I do see a lot of notebooks being handed over to try and get them out into production, and data scientists maybe think it's a week of time to do that.
So is that still a big pain point then, that you have people doing things in Jupyter notebooks, and that's the version of it worked on my machine, and then it gets given over to the software engineers?
Yeah, so we're trying to combat that by pairing engineers up with data scientists and sharing that, and cross-pollination and sharing that knowledge. So yeah, we're trying to influence like package management and stuff like that through Conda and things. So yeah, no, it's still a problem, but we're trying to chip away at it.
Very good, very good. Then question here, you showed some values around 0.7 for the regression models for your Stack Overflow dataset and said they weren't that great. What would you consider a good value for production models?
It just depends on the problem that you're trying to solve and what your business is happy with. So you probably want a higher value than like an accuracy of 70% for a business problem and production, maybe like 90%. But it's really it is key to the problem you're trying to solve and what you're happy with on the models.
Cool.
So.
And then you were talking there with issues with historical data where it could be too small or there could be biases in there and so on. So in your experience, how many ethical issues does that raise, day to day?
Yeah, so I think, yeah, I haven't been too much involved with anything that's been ethically, that I've thought has been ethically wrong in Liberty IT, but I think you just need to be mindful. Like some of the stuff that, some of the data that we can collect is maybe coming from external sources, and we're using that to determine things about our customers. So it's just really, are the customers aware that you're getting that external data on them, and that you're using that, and making sure that you're being compliant with all the rules and regulations, and just stopping to think, is what you're doing right. In the projects I've not been too involved on that side of it in my work, but it is something that I know that's being thought about, wider in the organization.
Cool. Yep. And then finally, you were talking there about feedback loops and, monitoring the models and models incorporating, the changes in the real world and so on. Is there any danger of getting what you used to have in automated trading systems, where they start trading with one another and then suddenly they start selling like mad, or, is there any danger of an unfortunate fast feedback loop and then we're in the insurance industry equivalent of Skynet or something like that?
Mostly at the minute, because it's quite new, it's usually a human that has to check the model, and so it doesn't just get pushed out into production without a human checking it and assessing it. So yeah, the feedback loops are kind of there, partially automated, but it's usually there's still human intervention to ensure that we're not doing anything crazy.
Cool. That's reassuring to know. Very good. So if I can thank you so much and dismiss you for now. And if I can ask Dani to step up for our fourth talk of the day. Hi there. The floor is all yours. I think you're still muted there. And we're good, I think.
Hello, can you hear me now? I take this as a yes. So, hello, and thank you for having me here today. It is a great event. It's my first bash, and I've learned a lot. I hope that I will be a regular bash attendee, and so one day I will meet you in person. So, thank you again for this opportunity. As you know by now, my name is Dani. My main skill set is evolving around mathematics. Apologies for that. I'm just learning to use tech. Is evolving around mathematics, and to my defense, I can make coffee and boil pasta, expanding my skill set there. I understand the world mainly using maths and logic, and this is why I get in trouble sometimes. Now less often than before, because I update my knowledge base, and experience comes with age. Here is an AI joke for you, right here. I will talk about agent resource allocation in different environmental settings. I am going to use the corporate environment as a paradigm for the model I am going to describe. And the reason that I chose this instead of another domain where this application might be relevant as well, let's say resource allocation in computational systems or in a Bitcoin mining situation. As I said, I selected this scenario, this premise, because I want to use a case with which we are all familiar with to some level. Also, this case helps me to demonstrate the limitations of this approach easier, especially when applied in complex systems, and a human system is a complex system. So, having said that, please let me state that I do not think that people are equations. I am not going to attempt to convert the human decision-making to an equation. And all I need is the input and the output. I understand that this might be considered an oversimplification in certain applications, but in this case, I do not need the motive. I do not need to know why an agent, a person, a computer is making this decision. I only want to know the potential outcome, and I think I can get away with this at this stage. Give it 6 months, and probably I will not be able to get away with this, and my application will become more limited, so it will have only limited cases. So far, I'm good. So Let me start with defining the problem. A team is a system and it comprises agents. The team has a goal. Let's say that the team has to deliver a project in a specified amount of time with set resources. The agents are the participants of the team, or whatever you want to put in your case, are aware of the resources and of their allocation, and they can communicate and exchange resources. For example, at work, if I have some free time, I can help another colleague with their task, and that is a collaborative scenario. However, as an agent, I have another goal, and sometimes I refer to it as a selfish goal. My goal can be aligned with the team's goal. For example, if I use all my resources towards the team's delivery, I will get rewarded. My goal depends on the welfare and the performance of the team. Excellent. My goal might not be aligned at all. For example, I want to use some or all my resources, ensuring that another agent does not deliver, or use another agent's outcome and ensure that I will get rewarded. Therefore, the team's goal does not strictly align with mine, or at all. In real life, the truth is somewhere in between, and I just presented two extreme cases. I can't help my colleagues all the time, and I can't be competitive all the time. So in order for my system to work at first stage, I made some assumptions regarding the agents and the system. And this is how I set the domain. The agents are utility-based agents. I will explain what a utility-based agent is later. The agents can collaborate and exchange information, but the information they can disclose to each other can be true, partial, or false, depending on their own goal. So, in short, we can say that agents can lie. The system can penalize agents based on set criteria. It's the rules of the game. That is, if you don't meet the criteria, then expect this type of penalty, either lack of reward, which is a non-zero-sum game, you don't lose anything, or removal, this is a zero-sum game. Someone gets 1, someone gets a -1. So the agents are aware of these criteria. 100%, there is no hidden agenda. So they know how the system operates, they know what the goal is, and they can adjust their behavior. The system can change the criteria, but there should be enough time to allow the agents to adapt. And I just saw that I made a typo on my PowerPoint, so that's embarrassing. So this is a bit tricky because some agents adapt slower than others. So in general, an agent that can adapt faster to the change, that is modify their behavior based on the new environments. And by behavior, I don't only mean their performance according to the goal of the system, but also their performance according to their own goal. They have better chances of reward. I run a distributed computational system in my room, and I found out, among other things that didn't work, that there will always be an agent that will take longer to respond to change. That agent might be a person, it might be a Raspberry Pi, it might be a laptop called a Pentium 1. So now I can go on and define the utility-based agent. Utility is the performance measure that allows a comparison of the different states based on how happy the agent will be in that state. So the utility-based agent, as you can see on the left-hand side, maintains a utility function, which the agent tries to maximize based on the performance measure. So in this case is a goal. The performance measure is set by the agent itself. So the agent can pay more attention to its own personal goal or to the goal of the team, depending on the alignment we discussed before. In this example, the utility function is simple, and we have 3 states. We have a happy agent where the goals are aligned. So the performance of the agent focuses on the advancements of the team towards the goal. We have a agent in the middle, or as I call it, meh agent. Since this is not published yet, I can call it meh agent. Goals are partially aligned. This is an agent with high volatility. Based on a Bernoulli equation, the agent might shrink more on one way or another. So we can have a distribution, a randomization of swing, or we can have a toss of a coin problem, 0 or 1. And then we have the selfish agent, where the goals are not aligned at all, where the agent can say, I don't care about the well-being of the team. I have my own agenda. I will follow that. I selected the utility-based agent because they are more adaptable to changing environments. They can make rational decisions in scenarios where there is not certain if the overall goal will be achieved. So my main goal for this was the adaptability of the utility-based agent. And what went wrong and what is still going wrong is that modeling it in Python is very, very challenging. But I will get back to that later. The utility-based agent specifies the appropriate trade-off if the goals are conflicting, or the appropriate likelihood of success of each goal. I wrote 2 different behaviors, and I looked for examples in literature and philosophy to say things nicely. So type 1 is an agent which wants to fulfill their independent goal no matter what. I found this definition by Ayn Rand. It says, every man is an end in himself, not a means to the ends of others. He must live for his own sake, neither sacrificing himself to others, nor sacrificing others to himself. He must work for his rational self-interest, with the achievement of his own happiness as the highest moral purpose of his life. When I quote Ayn Rand, I just want to point out that she benefited from state aid through her life. So I'm very well aware of the problematic of this whole discourse. And the fact that I'm using it as an example, it doesn't mean that it reflects my personal opinions, as in everything that is quoted here. Please don't come at me. This is the closest description that I could find for the agent that focuses solely on their own goal. If it fits, if it matches the team's goal, then great. But if it doesn't, then we might have a problem. In type 2, we acknowledge that the goal, in fact, is subjective and might be defined by a more complex system. In this case, the agent is more susceptible into using not only its own knowledge base to inform its decision, but also information coming from other knowledge bases available to them, such as information about other agents, and also it has a likelihood of using another knowledge base's information to inform his decision. Because according to Solomon, who tries to use game theory as a model for business and business ethics, business, like most of human life, is motivated not by self-interest, but by a complex of what Adam Smith called fellow feelings and sympathy, affection and vulnerability, a sense of shame and a sense of honor, love and friendship, animosity and resentment, and 100 more emotions and attitudes. And this is where I have a little voice in my head saying, good luck putting that into an equation. I can't. Then I ask myself, how can I get there? What is game theory at the end of the day? And how can I use this to inform my planning schedule to see what happens in different scenarios? Game theory provides the tool to incorporate factors determined by human nature and behavior, thus making game theory more appropriate to simulate not only economical systems, I mean, it's used there already, but also new domains such as neuroscience, psychology, and sociology. By assigning the parameters above and trying to simulate different scenarios, I am making a basic attempt to predict the outcome, that is the goal fulfillment or not, where at the same time I observe the agent's performance and behavior. I want to draw your attention to the collaboration between agents. For this, I'm going to use the prisoner's dilemma, and it is as follows. Two people are arrested and placed in different detainment units without any means to communicate with each other. They will be interrogated separately, and depending on the answers they provide, we have 4 potential outcomes. Both of prisoners betray each other, so prisoner A betrays prisoner B, and vice versa. Both of them spend 3 years in prison. If prisoner A remains silent and prisoner B betrays, then prisoner A goes to prison for 5 years, prisoner B gets to walk free. If prisoner A betrays prisoner B, prisoner A gets to walk free and prisoner B stays in prison for 5 years. However, if both defect and remain silent, then they will only spend 1 year in prison each. Based on the prisoner's dilemma, I try to simulate the route to rewards problem. Again, I have 4 different scenarios. That is now the evaluation that the system applies to the agent. So if we can have employer A and employer B both promoted, or we can have cases that are one is not promoted and the other one is promoted and vice versa. So this becomes a game between the employees now. This is a non-zero sum case. That means the win of one agent does not equal the loss of one agent. The agent that will not be rewarded will have no change in its existing situation. There can be another case when this becomes a zero-sum case, which means that some agents are removed from the system, and this is a zero-sum game. If I have an agent, let's say, performing 2, and an agent performing -1, and the overall system performance needs to be 1, I can safely remove the -1 agent to have, because it gives me losses. It's a little bit like a very simplified stock market version. Time is not taken into account there. The difference between this problem and the prisoner's dilemma is that the agents can communicate in this case. However, as we said before, the information that they exchange might not be true. So a conservative approach is to take this problem in bad faith, assume no communication between agents, and turn this into a non-cooperative game, which means like a highly competitive environment. So I have a system, I defined the rules, or I defined the system domain. Now I need a way to measure the performance of the system. I'm going to use the price of anarchy as a metric. It has been introduced by Koutsoupias and Papadimitriou. It is defined as the ratio between the worst possible Nash equilibrium and the social optimum. And this is a measure of the effectiveness of the system. So it is what is the worst that can happen compared to the desired situation. Let's apply this case to the prisoner's dilemma. We define as social optimum the case where both people are going to jail because they did something bad according to the existing laws of the system. Therefore, the worst case for the definition is for them to spend the least time in jail. We have the worst case equilibrium is the green 1 + 1, and social optimum is 3 + 3, so it's 1/3. So that is the value of the price of anarchy. I defined the social optimum strictly and without taking into consideration what the agents think that the social optimum is. So it doesn't matter what the agent thinks at this stage, it matters how the system evaluates the performance. And the agents in the prisoner's dilemma knew how the system operated. The reason for this is that I want to use the price of anarchy as a metric for the system's performance and not for the agent's self-evaluation. What an agent consists as an optimum case is derived by its internal goal definition, which we described above. I ran a small, I forgot to show you this great slide. I ran a small set of scenarios with 6 agents, and the overall conclusion was that the higher the price of anarchy, the faster the system degrades. That happens because the social optimum becomes the worst case scenario, and therefore the price of anarchy approaches 1. We really want it to be less than 1, ideally less than 0.5, as low as possible. Initially, I used Python, as I said before, to run this analysis. However, now I am moving to MAPDDL, which is multi-agent planning domain definition language. And planning domain definition language is quite nice. It's easy. It's more readable by humans. And at this point, I want to highlight that the fact that the code is readable by humans doesn't mean that you shouldn't write the documentation of your code. Please document your code. Thank you. And also allows for more flexibility. MAPDDL allows for easier assignment of different actions to different agents and different goals and metrics to the agents. So I can overcomplicate things, hopefully, as much as I like. This talk will be online, and in 6 months, I might come back and eat my words. So far, I examined the following scenarios. Change of scope. When the team goal changes, it takes longer for the system to degrade. This happens because there is an adaptation period where the agents that are more flexible and comprise the majority of the team are working towards the team's goal while reevaluating their own goal. So the selfish agents are behaving the same. We're looking at the type 2 agents, how they behave. After the adjustment period, some agents are dropping out or add to the system's degradation due to failure to adapt. Remember that the system defines if the agent should drop out. So if the system says you're not performing, get out, then you have less agents to work and you have to reevaluate the situation. If you keep the agents, then you might have some degradation over time, but then eventually the agent will catch up. So you need to see how much time you have there. Constant rate of reward. If I keep a constant rate of reward, the rules are clear, set in stone, then the price of anarchy value remains constant because the agents know the rules of the game. Relatively constant because you always have an agent that will drop out or something that will go wrong. But in general, it oscillates around a point. If I introduce a new agent, then I have for a good while a constant price of anarchy value, and then I see a fast decline. And this was not something that I expected in my very simple 6-agent, project. I think that the last scenario might be a case of Bryce's paradox. Bryce is a mathematician that stated that if I add extra capacity to a root network, so I will make a new road, then the cars will choose the easiest route and they will reduce the shortcut, if you want, and they will reduce the overall performance. That is because the Nash equilibrium of this system is not necessarily optimum. So my question will be, should I back engineer from an optimum Nash equilibrium and see how the shortcuts will be optimum? Will this work and how long will it take to achieve that? The network changes, introduces a new structure, and then we have a new prisoner's dilemma. Another scenario that might lead to a Bryce paradox is to add shortcuts to the routes to rewards. And I will leave this to your imagination to see what can go wrong in any scenario you chose. As this is a work in progress, after my lengthy break, I will focus on the following. What happens when an agent changes mid-tournament, like drastically, change of mind? How will the system adapt to this shock change? A note to self there is use functions instead of tuples and get on with MAPDDL because Python hurts me. It's not that it is I have a complaint against using Python as a programming language, but I think that to make this application easier and faster, because I want results and I want to be able to change things fast, I think I will use MAPDDL. And a big thing is, how can I model the likelihood of hierarchical bases as a knowledge base? And I think this is all from me. Please note that this work is based on some assignments that I did for my master's at the University of Huddersfield, where I'm studying artificial intelligence. And I will pass the virtual mic to Garth.
Thank you so much. That was absolutely fascinating. And with your permission, I propose to put Met Agent on my business card from now on. I think that's a perfect description. Yeah. So I had a feeling this talk might blow my mind. So at this point, I would like to invite all the other speakers back on as well to help me gang up on Dani and ask some intelligent questions. So any volunteers to go first? Any thoughts?
You're putting me up 3 of the smartest people in 2 countries, by the way. No pressure for me. To give you an example, I tried to solve Fran's games in her book, which is somewhere about the house, and I do enjoy programming the turtle out of the bag way too much. So, yeah.
Can't beat a bit of random.
I used the randomization function in this problem because, as I said, I can't predict behavior. I chose how much the functions will be random, and this sometimes broke the system. So I had to go back to your book and refer to that for this. So it's a full circle.
So I've got so my background is half academic, half company, and so my academic part I like looking at pinheads of pinheads. There's no application to anything because that's fun. The company part's tricky because you then need to apply it. So you did lots of nice game theory, and I don't really understand game theory because it's not my area. But can you give us a few examples of where this is used in real life? You know, where are companies using it? You know, so if I was a nice insurance company and I wanted to do this, what's the sort of problems I'm going to start looking at?
At the moment, it sits in a purely academic situation because this is not part of my paid job. It's part of my work at the university. I wrote some assignments on it, and then I overfocused, and then this came up, and then I'm going to follow this, hopefully, with supervisor's approval as a dissertation. So I don't know anything about the insurance world either. I don't want to mislead you, but I can share resources with you. And you can pick and choose, or you can make recommendations on running the scenarios. How does this sound?
When you're in a position to teach agile project management with Scrum and game theory, I will be at your door with a blank check and a pleading expression. You know, so it's absolutely fascinating stuff. Yeah. Any other questions there?
Yeah, it sounded it was really interesting, Dani, and it was a bit above my head at times, and it sounded quite theoretical, you know, all these scenarios. But have you been able to kind of see if, like, what you're seeing with your simulations, if that matches up with anything in the real world at all?
I've tried this with some distributed systems, which are on the mess that you saw before we went live, and I had some success. I had the predicted Nash equilibrium simulated with real-world computational problems with Raspberry Pi sticking out of everything, and some of them were. So this was my situation of, a bad thing. I learned from this. But unfortunately, when it comes to real-life examples like corporate situations, I'm not very happy to go and task and recommend this as a system to improve performance or to monitor employees. It's mostly like a theoretical behavioral game, if you want to, because, as I said, people are not agents. So I can tell you, and judging for myself, that in a good day, I wake up, I brush my teeth, and I write 50 lines of code and have a Confluence page. Success. How can I simulate this for 50 Danis across a company? That becomes, you can't bug agents in human problems. This is what I'm trying to highlight here. And this is where you probably need very smart randomization in your utility function. I think I looked up a little bit at a Bitcoin mining situation, and I think I will move towards to more robust computational systems and leave the humans behind. The reason why I chose humans is that we can all relate to the examples rather than me bombarding you with maths and saying, and if I use a CPU allocation here of 50%, then this agent will do this, and this will have to do 20% allocation. So I didn't want to bore you with a lot of CPU allocation graphs, if that's okay.
Fair enough. Very good. So let me just open the floor now and ask any of the speakers if they'd like to ask a question to any of the others about anything that we've heard so far today. Anybody curious? Nope. Well, let me ask one in closing then. So for the question that you always hate to answer, but I'm going to ask it anyway. So where do you think ML is going to be in 5 years? Where do you think we'll have moved to if we do this event in 5 years' time? So what do you think the most significant advancement or change will be? Anybody care to go first? Colin, I'm going to pick on you for no particular reason.
Should at least be Fran because she went first. I quite like the idea of sort of the auto ML. The idea that data scientists now sort of spend the time writing for loops, looping over models, whilst keeping me in a job is not the most productive time. And what I don't know is what that free time will allow other people to do, so there's always that fear of computers taking my job, oh dear. But I think in our industry, it'll free up more interesting, different problems and just sort of take away the mundane part. In the same way we don't do multiplication or matrix inversion using paper and pen, the computer does that. Yeah.
And we don't write parsers anymore, write TCP IP stacks or stuff like that. Yeah.
We just find other problems.
Cool. Very good. Vicky, do you want to take a swing at it there?
Yeah. I kind of liked what Colin said. I think AutoML is probably going to become a bit bigger, hopefully. And I hope that there's just more tools and frameworks out there to really help data scientists, get their models to production and help them build, in a good way and stuff like that. And I think there'll be maybe more engineers as well getting involved in the data science aspect. So I see it growing and being a big part of software engineering world, and we'll maybe be focusing on slightly different problems than what we have in the past for our jobs.
Cool. Very good. Fran, over to you.
That's a huge unanswerable question, but I can see a space where we start moving away from ML being used to mean kind of stats and curve fitting and start rediscovering some of the original places that was to do with game playing and stuff. I also see moves in terms of creative industries and generating music and that kind of creative side of things and artworks, and I wonder if that moves us into some of the hard AI and we end up near robots and physical place rather than the software place purely. I can see a lot of potential for things mixing up and changing as time goes on. Once we stop doing all these for loops and things, like Colin said, let's move things on.
Cool, very good. And Dani, back to you again. What do you think?
I think that during the next 5 years, we need to have a conversation about ethics in machine learning and AI. And this is what I wanted to highlight in my talk as well, that can we, and leave it as an open question. I presented you a problem in a premise, which is very complicated. Is it ethical? Is it nice? Does it make the world a better place? So I think that in 5 years, what I hope that we will do is put ethical standards and have a very serious talk about how we're improving humanity with this. And about seeing a talk about, an AI plant robot that landed with a drone and saved someone's life in a remote island. That's what I want to see, and that's my dream and hopes.
Cool. Brilliant, and a wonderful way, I think, to close, because it's just gone 2:00 and we are perfectly on time. So thank you so much indeed for your talks. They have all been excellent. Thank you very much. So if I can dismiss you all at this point, one final time, and it only remains to say thank you again to our speakers. Thank you very much to Zara and Ryan for all the hard work that they do in the background. And thank you to everybody who attended and for all the questions. And we look forward to seeing you in the next event. So thank you very much indeed. And see you in the next batch.